Hello friends, in our previous lecture we considered two coordinate systems, and towards the end of the lecture we claimed that one of the coordinate system is rather the inverse of another. So the two coordinate system which we considered were polar coordinate system and two-dimensional Cartesian coordinate system. Now when you consider a point in a two-dimensional space, let this be the point. In case of the polar coordinate system, you begin by considering an origin and you drop or consider the distance between the origin and the point. And in order to ensure that you are able to locate the point exactly in the circle that can be subscribed using the distance between the origin and the point, you introduce an angle theta. And correspondingly, the position of your point can be described in terms of r and theta. Now, in order to establish a relation between this polar coordinate and the Cartesian coordinates, whose coordinates are x and y, we superimposed the Cartesian coordinates onto this polar coordinate system in such a way that even though in the immediates the origins are not coinciding, we superimposed in such a way that it is on the origin of the polar coordinate coincides with the origin of the two-dimensional Cartesian system. So this will be our x-axis and this will be our y-axis. Now we were able to establish a relation between the coordinates of the Cartesian coordinates and the coordinates of the polar coordinate system. Now if you consider the coordinates of the polar system, r can be expressed in terms of x and y, and this r would be, rather it can be expressed as x, or rather x square plus y square, the whole power 1 by 2, or the square root of x square plus y square. And the theta in terms of x and y would be tan inverse of y by x. In the same way, the Cartesian coordinates can be also expressed in terms of the polar coordinates. This would be r cos theta, and y in terms of r and sine would be r sin theta. So I hope, so this is what how we will be able to relate the coordinates of two different systems, and we have x and y represented in terms of r and theta, and r and theta represented in terms of x and y. Now what we did in the previous lecture was we showed that when r, if it is represented as a function of x and y, and these x and y are in terms a function of r and theta, then we would be able to recover through this relation this r as an independent variable. So initially we treat r as a function of x and y, and our x and y are in turn a function of r and theta. If we do that, we will be able to recover r. The same way, if we began by considering theta as a function of x and y, and this x and y are again in turn a function of r and theta, if you treat the x and y again in turn of as a function of r and theta, we will be able to recover theta. So this, since we are able to recover the r and theta, starting with treating them as a function, and by considering the relation between the x and y to that of r and theta, since we are able to translate this function and recover the corresponding independent variable, the corresponding independent coordinate, we assumed that, or we considered, or we claimed that these two coordinate systems, that is polar and Cartesian coordinate systems, the way we have represented here, are inverse of each other. So what essentially, to arrive at this inverse relation, to describe this inverse relation, what essentially we did was we considered one of the coordinate of the polar coordinate system and then expressed it as a function of x and y. So x and y, the coordinates of the Cartesian coordinate system. These x and y, we in turn treated it in the form of a function that is dependent on the independent variables, or the independent variables r and theta, which are the coordinates of the polar system. Now when we have such a function within the function, then we are able to recover one independent variable that is similar to that of our original function. Now when this condition is satisfied, these two coordinate systems that we are considering, these two coordinate systems that we are relating using a function within a function, these two coordinate systems are inverse of each other. Now, what essentially we will try to do is, now that we have this relation here, this relation we have, so this is a well-known relation, you would have come across this in your early semesters. Now we will try to substantiate this claim. We will try to rather ensure that this inverse property, or we will, through some numerical operation, through some numerical treatment, we will try to ensure that this inverse relation holds true. We will try to substantiate the claim that when we use this treatment of involving a function within a function, if we are able to recover the original function or recover the original function as that of a variable, then the old coordinate system, the combination of coordinate system that we involved is inverse. This we will try to prove by considering an additional numerical operations. Now, in order to do that, let us begin with the consideration of expressing r as a function of x and y and theta as a function of x and y. Now, this we have already we have expanded r as a function of x and y here and theta as a function of x and y here. And in the same, so now what can be done is, it is possible for us now to consider in the same way x as a function of r and theta and y as a function of r and theta. We are not considering a function within a function, we are just considering x as a function of r and theta, y as a function of r and theta. Now, r as a function of x and y, theta as a function of x and y. So instead of writing instead of expressing this in terms of a relation, we are just considering the function r in terms of x in terms of r and theta, y in terms of r and theta, r in terms of x and y, theta in terms of x and y. Now, let us try to consider the derivative of x, y in terms of r and theta and r and theta in terms of x and y. So let us first consider the derivative of x in terms of r and theta and y in terms of r and theta and express it in the form of a matrix. Now, let us consider x, y and express it in terms of matrix. Let us refer to this as J1. What we are considering is x and y as a derivative of x with respect to r and theta, y with respect to r and theta, and expressing in terms of matrix. So what essentially we are doing is dou x by dou r, dou x by dou theta, dou y by dou r, and dou y by dou theta. Now this is a matrix that you might be familiar with. This is nothing but the Jacobian matrix. So Jacobian matrix, it considers the, in this Jacobian matrix J1, it considers the partial derivatives of x and y with respect to r and theta. Now let us consider another Jacobian matrix J2, which includes the partial derivatives r and theta with respect to x and y. So it will be dou r by dou x and dou r by dou y, dou theta by dou x and dou theta by dou y. Now we have established a relation between x and r, x and theta, y and r, y and theta. In the same way, we have established a relationship between r and x, r and y, theta and x, and theta and y. So therefore, we will be able to substitute the corresponding, we will be able to rather quantify these derivatives from the relations. So these relations are over here. From these relations, we will be able to say, or we will be rather able to replace these individual elements. So these partial derivatives, we will be able to really replace it with absolute values. Now when you consider dou x by dou r and consider this relation, the partial derivative of x with respect to r, in this relation what we would end up having is cos theta. And now in the same way, dou x by dou theta. So let me use a different color to mention it. So we have x, the partial derivative of x with respect to r, and in order to find this partial derivative, we consider this expression here. So dou x by dou r would be cos theta, and dou x by dou theta, so dou x by dou theta would be minus r sin theta. And in the same way, now we need to consider dou y by dou r. So we need to consider this expression dou y by dou r. So dou y by dou r would be sin theta, and dou y by dou theta would be r cos theta. So ultimately, this Jacobian J1 can be written as cos theta minus r sin theta, and sin theta r cos theta. So the way we arrived at it, this Jacobian is, all that we have done is we have replaced these partial derivatives with respect to that of the corresponding cos and sin theta, the corresponding terms that involves r and theta. Okay, so that we were able to do by considering this relation. So the same can be extended for r and the derivative, partial derivative r with respect to x, with respect to y, and so partial derivatives r and theta with respect to x and y, the same treatment can be adopted. And when we do that, so what needs to be done is we need to rather consider the partial derivative of r here with respect to x. Now when we do that, the way we will be able to arrive at the expression is now this expression dou r by dou x. When we consider this, when you want to estimate this partial derivative of r with respect to x from this expression here, we would end up with the first term would be of this form, x by x square plus y square the whole power 1 by 2. So what we have done is we have the expression that relates r, x and y. So from that expression we were able to arrive at this. So we were able to take the partial derivative of this expression with respect to x, and then we were able to arrive at the first term here. The similar way we will be able to reach the second term or arrive at the second term, which would be x square plus y by x square plus y square the whole power 1 by 2. Now the r theta by or dou theta by dou x will be of this form. Of course, there will be more tan inverse, we need to extend it and we need to take the derivative of it, and it would be of the form minus y x square plus y square, and this term would be x by x square plus y square. So what essentially we have done is we have translated these partial derivatives to exact terms involving x and y. Now it is possible for us now to substitute this, replace x and y in terms of r and theta. So we have a relation that relates x and y. So we have expression that relates x to r and theta and y to r and theta. So this x is nothing but r cos theta and y is r sin theta. So when we substitute for x, now in this expression, the one in red, what essentially we can do is we can substitute the x as r cos theta and y as r sin theta. Now when we do that, when we substitute x and y, replace x and y with r cos theta and r sin theta, then the J2 matrix would be of this form: cos theta sin theta minus sin theta by r and cos theta by r. So what essentially we have done is we have an expression for r in terms of x and y and theta in terms of x and y. So using that expression, we were able to translate the J2 Jacobian into a matrix that involves x and y alone. Now we also have a relation where the x are equated to that of r and theta, and y is equated to that of, so x and y are equated to that of r and theta. Now using that relation, we expressed the Jacobian J2 in terms of r and theta. Now let us consider the product of J1 and J2. Let us consider the product of J1 and J2. Now J1 is cos theta minus r sin theta. So the J1 is cos theta minus r sin theta or cos theta. So it's just I'm rewriting this expression here, the J1 matrix. It is cos theta minus r sin theta and sin theta or cos theta. So that's exactly what I've written now. Yes. Now the J2 is cos theta sin theta minus sin theta by r, or rather minus sin theta by r, and cos theta. This is cos theta by r. So ideally it is so this r here, it is for whole. It is not just for theta by r, it is for the whole cos theta by r. So the accurate way of writing is it's being done here. Now when you consider this matrix multiplication, what we observe is this would turn into the first term. The first here the first term would be cos square theta plus sin square theta. So it will be cos square theta and plus sin square theta. And the second term then would be sin theta cos theta minus sin theta cos theta. So the second term would be sin theta cos theta minus sine theta rather minus sine theta cos theta. Now in the row below, the first term would be sine theta cos theta minus sine theta cos theta. So what essentially we are doing is we are multiplying this sine theta to that of cos theta and taking the sum with respect to r cos theta with respect to this term. And the second term would be sine square theta plus cos square theta. So when you do the matrix multiplication for the second term in the bottom row, it would be sine square theta and plus the r square plus the cos square theta. So what ultimately we would end up with is the product of the Jacobian 1 and 2 is nothing but 1 0 0, or rather we can write it as I, which is the identity matrix 1 0 0 1. Okay, and ultimately, so this relation means that Jacobian 1 is nothing but the inverse of Jacobian 2. So what essentially we have arrived at is, we began by considering two coordinate system involving x, y, r and theta. Now we have established, by superimposing these two, we have established or we have related coordinates of each of the system to the coordinates of the other system. So we have expressed x in terms of r and theta, y in terms of r and theta. In addition to that, we have expressed r in terms of x and y and theta in terms of x and y. Now once we were able to do this, then we consider, so this is something that we covered in the previous lecture. So when you consider what we did in this lecture, what we did was we considered the partial derivatives of the coordinate system and in terms of, and expressed it as a Jacobian. When we expressed these partial derivatives in terms of Jacobian, we were able to arrive at this matrix here, and this first matrix, that is the Jacobian 1, wherein we are considering the partial derivatives of the Cartesian with respect to the polar. We were able to arrive at this expression here in terms of r and theta. So Cartesian with respect to polar, we were able to arrive at this expression or arrive at this matrix here. Now when we consider the polar coordinates expressed in terms of Cartesian and took the derivative of it and expressed in terms of Cartesian, Jacobian matrix or Jacobian, what we ended up having was a matrix of this form, which is written in terms of x and y. Now in order to ensure that, in order to handle both these matrices, in order to ensure that these matrices have the same independent variable, we translated the x and y, we changed the x and y, we rewrote the x and y in terms of r and theta, we ended up with this matrix here. So one matrix J1, the Cartesian expressed, or the derivative of Cartesian in terms of polar. The second matrix, the derivative of the polar in terms of the Cartesian. And now in order to treat both these Cartesian in the same framework, we changed or we replaced x and y with r and theta. And when we did that, when we changed the second Jacobian from x and y to r and theta, and when we took the product of first and second Jacobian, we were able to show that, we also saw that the product of this Jacobian yields an identity matrix, thereby revealing that Jacobian of one coordinate system is rather the inverse of another coordinate system. Now it might rather be a huge question to us, why would we have to take the Jacobian of a given coordinate system? Why should we, so once we have established a relation between the coordinates of one system to that of the another system, why should we have to take the Jacobian of it? This is a critical point that will help us understand how we can generally describe a coordinate system. Now the taking the Jacobian of it, so what essentially Jacobian involves is taking the partial derivative of the coordinates of one system with respect to another system. So taking the partial derivative of the coordinates of one system is what principally the Jacobian involves. Now the reason why we take this Jacobian will become clear when we attempt to describe the coordinate system not as x, y and z, r, theta and phi. When we attempt to describe the coordinate system in a generic way, the reason for taking the partition will become absolute, or taking the Jacobian or taking the partial derivative will become absolutely clear. So in order to, before we reach that point of arriving or describing a given coordinate system in a generic way, not involving x and y and z, which have a predefined predefined connotation or predefined attribution to it, let us try to rather have a generalized understanding of these inverse between these coordinate systems. So far we have considered two coordinate systems, that is polar and two-dimensional Cartesian, and we were able to discuss about the inverse relation between them, and how when we have this inverse relation, or how this inverse relation can be understood when we consider the partial derivative of each of these coordinates. Now let us try to, instead of focusing on this predefined coordinate system, these coordinate systems that have a well-established meaning associated with it, let us consider a generic combinations of coordinate system. So let us assume a coordinate systems I, j and k, and I prime, j prime and k prime. Let us consider these coordinate system I, j, k, and I prime, j prime and k prime. Now these are two different coordinate systems, and I, j, k and I prime, j prime, k prime, they indicate the coordinates of these corresponding systems. Now let us assume that these are inverse of each other. These coordinates are inverse of each other. So what I mean by that is, let us assume that there exists a relation wherein the I can be expressed in terms of I prime, j prime, k prime. The j can be expressed in terms of I prime, j prime, k prime, and the k can be expressed in terms of I prime, j prime and k prime. So what essentially we have is two coordinate system, and each coordinates of these system can be replaced by, or can be expressed in terms of the coordinates of the other system. So we have a coordinate system A, we have the coordinate system B. Each coordinates of the system A can be expressed in terms of coordinates of system B. The same way, each coordinates of system B can be expressed in terms of the coordinates of system A. So correspondingly, I prime would be, I can be expressed in terms of I, j and k. J prime can be expressed in terms of I, j and k, and k prime would be expressed in terms of I, j and k. Now when we consider, as we considered earlier, a function within the function, when I consider I prime as a function of I, j and k, and these I, j and k are in turn a function of I prime, j prime and k prime, and j is in turn a function of I prime, j prime and k prime, and k is in turn a function of I prime, j prime and k prime. Now when I consider such a treatment, I am expressing a coordinate I prime in terms of another coordinate system I, j and k, and this I, j and k, the coordinates of another system, are also a function of I prime, j prime and k prime. Then I would be able to recover my independent variable I prime. Now the same can be extended for the j prime, where the j prime can be expressed in terms of as a function of I, j and k, and this I as a function of I prime, j prime and k prime, j as a function of I prime, j prime, so prime functions, and k as a function of I prime, j prime and k prime. And when I treat my function of j prime in this manner, I will be able to recover an independent variable j prime. In the same way, k prime, if I handle it as a function of I, which is again a function of the prime variables, j, which is again a function of the prime variables, k as a function of the prime variables, I will be able to recover the k prime as an independent variable, starting as a function of a function, recovering of an independent variable. Now, what can be done is, in the same way, we will be able to recover the I, and when we treat I as a function of a function, we will also be able to recover I as well. Now, so whatever we have been able to do for I prime, j prime and k prime can also be extended for I as well. So it can also be extended for I as well, and I, j, k as well. So what essentially we will have is, we will have a function within a function. So whatever numerical treatment we are performing for the ij's and k's can be extended to these. Now guys, you might be wondering why we are taking the pain of expressing all these. So what essentially we have done is we have extended our consideration to three-dimensional system, and you might be wondering why we are taking the pain of doing all this. Even though this might seem absolutely vague and purely theoretical, this lends itself into understanding one important aspect of a numerical treatment that is vital for our materials research. So whatever we are doing right now will lend itself to one of our module and one of the numerical technique we need to be familiar with when we are doing materials research. So therefore, please bear with me. Please follow the thought at least on where things are going and how we are handling these different coordinate system. So okay, so I, j, k, different coordinate system, I prime, k prime, j prime, a different coordinate system. We are treating the coordinates of one system as a function of the other system, and in turn when you are treating it as the original function of the existing system, then we will be able to change the function to that of the independent variable. So that is essentially what we have done. So this we have considered using r and theta to make ourselves comfortable with what this expression here means. Now if you are comfortable with that expression, then you will be able to make sense out of these three terms here. Okay, now what we have is we have an expression. So this is, we are able to establish this by expressing each of these coordinate system or each of these coordinates in terms of the another coordinate system. Now when you consider the original expression of I being, or I prime being the function of I, j and k, j prime being the function of I, j and k, and k prime being the function of I, j and k, it is possible, similar to that of r and theta, it is possible for us to consider. So in this case what we have done is we have recovered, so from this expression here, by considering a and b coordinate system, we have recovered the I prime independent variable by beginning with I prime as a function. So that is all we have done. However, we have also established that there exists a relation in addition to this recovering or starting with I prime of a function and recovering it as a variable. We have also established there exists a relationship between, so it can, the I prime can be expressed as I, j and k, and j prime, so on and so forth. So this relation we have established. So what it means is that we will be able now to express the partial derivative of I prime in terms of these, so partial derivative of the coordinates of the prime coordinates in terms of the coordinates associated with the other system. So we will be able to describe the partial derivative of the prime coordinates with respect to the other coordinate. So therefore, using the same Jacobian matrix, we will be able to express the partial derivatives of I prime with respect to I, the partial derivative of j prime, or rather I prime with respect to j, the partial derivative of I prime with respect to k. The same way, the second row would involve the partial derivative of j prime with respect to I, the partial derivative of j prime with respect to j, the partial derivative of j prime with respect to k. The third row then would be the partial derivative of k prime with respect to I, the partial derivative of k prime with respect to k, and the partial derivative of the k prime with respect to k. So this is one Jacobian that we are able to establish from this relation here. Now we also have, so the other Jacobian J2 will involve the coordinates I, j and k, coordinates I, j and k, which are expressed in terms of I prime, j prime and k prime. I prime, j prime and k prime. So these coordinates I, j and k are expressed as a function of the prime coordinates I prime, j prime and k prime. So the corresponding Jacobian then would be partial derivative of I with respect to I prime, partial derivative of I with respect to or j with respect to j I prime, or rather pardon me, j prime, partial derivative of I with respect to k prime, partial derivative of j with respect to I prime, the partial derivative of j with respect to j prime, the partial derivative of j with respect to k prime, and so on and so forth. A with respect to j prime, k with respect to k prime. Yeah. So what now we have is, we have established two Jacobian. One, considering the partial derivative of the prime coordinates with respect to the ijk coordinates. The second Jacobian is the partial derivative of ijk coordinates with respect to the prime coordinates. Now it is possible for us to consider the product of these two coordinates. Yes, it's going to be a bit difficult. We will try to rather simplify it. It is possible for us to consider the product of these two coordinates, J1, the Jacobian 1 and Jacobian 2. So this can be written as, so let us assume that the first element can be written as 1 1, can be written as 1 1, 1 2, 1 3. So let us express it as J11, J12, J13, and so on and so forth. So ultimately you will end up having J33 here. Okay. So what we have done is, the product of the two Jacobians, we have considered the matrix of it, and we have instead of expressing the whole terms, we are including all the terms. We have just considered J11, 12 and 13 and so on and so forth. So this then would be J21 and so on and so forth. I believe we were able to complete the dots. Now let us try to understand at least few of these elements. That is, let us try to understand what the J11 is. So J11 involves the summation and product of these row and this column here. So what J11 will then involve? So this would be, the J11 would be something like this. So we can write J11 as dou I prime by dou I and dou I by dou I prime plus dou I prime by dou j, dou I by, or rather dou j by dou I prime. So there is a prime here, dou I prime by dou I, so this term and the product of this term. The second is, and we sum it up with this term, the product of this term and this term, and finally we sum it up with the product of this term and this term. And when we do that, what we end up having is something like this. So we have dou I prime, dou j and dou j, dou I prime. And finally the final term that we have is dou I prime by dou k and dou k by dou I prime. So this is the expression for the first element J11. Now this expression here, J11, this expression here can also be arrived by considering this term here. From this term, from this equation, it is possible for us to gather, to estimate this first element. So the first, the expression that we are looking into, is this one. So it will be I prime, which is expressed in terms of as a function of I, j and k, and these I, j and k are in terms of function of I prime, j prime and k prime, and j in terms is a function of I prime, j prime and k prime, and k is a function of I prime, j prime and k prime. Now when we consider this, when we consider I prime as a function of a function, then we are able to recover I prime as an independent variable. Now when you consider the partial derivative, that is, when you consider dou I prime by dou I prime for this function of a function, then we can use the chain rule and express the dou I prime by dou I prime as dou I prime by dou I and dou I by dou I prime. So we can use the chain rule and expand, and we can arrive at the partial derivative of I prime with respect to itself as, so again this is a function, this is not an independent variable, this is a function. So partial derivative of I prime as a function with respect to the partial derivative. So I prime here is a function. So that distinction needs to be made. So on the left hand side what we have is a function, on the right hand side is an independent variable. So dou I prime as a function with respect to dou I prime as a variable. So this derivative we will be able to estimate by using the chain rule. So therefore it will be dou I prime by dou I and dou I by dou I prime. So this will be the first term. The second term would be dou I prime by dou j and dou j by dou I prime plus dou I prime by dou k by dou I prime. So this we have arrived at by considering the chain rule, and this is when you impose the chain rule in the left hand side of our expression. So the left hand side of our expression gives us this combination of terms. And when you consider the derivative of I prime with respect to I prime, so for the derivative of this term on the RHS, which is the independent variable with respect to itself, you will end up having 1. So therefore J11, the value of J11 would be equal to 1. So what essentially we have done is, we have considered the I prime as a function of a function, took the derivative of this I prime, which is a function of the function, with respect to the independent variable of I prime, and the right hand side of your expression then becomes, we can expand the right hand side of your expression using the chain rule, and this expansion, it coincides with J11, the first term of the product of these two Jacobian, and the value of it turns out to be 1. So now when you consider the second term J22, that is J12, so just J12 would be, so what essentially we would then have is the J12 would be, we need to consider rather the product of this row in this column here. So it will be of this form. So we will be having, or if you consider the J12 and all the partial derivatives that are involved, these would essentially mean that we are considering the partial derivative of this I prime, so this partial derivative of this I prime as a function of a function with respect to J prime. So what essentially the product of the, or the J12 means, what essentially J12 is, the J12 is nothing but the partial derivative of the I prime as a function with respect to the independent variable of J prime. So that is exactly what it would mean. So when you consider, when you write the J2, when you expand this J12, that is this term here, this element of the matrix J12, how it would look like is, it would be of this form, dou I prime by dou, so we start with dou I prime by dou I, and dou I by dou J prime plus dou I prime by dou J by dou J prime, dou I prime by dou K, and dou K by dou J prime. So this is what the element J12 would look like. So what essentially we have is dou I prime by dou I and the product of dou I by dou J prime plus, so these terms and these two terms. So let me use a different color. So this two terms, so dou I prime by dou I into dou I by dou J prime. Then we will have plus dou I prime by dou J plus on dou I prime by dou J and dou J by dou J prime. And the third term would be dou I prime by dou K and dou K by dou J prime. So that is exactly, I believe, what we have here. That is dou I prime by dou I into dou I by dou J prime, dou I prime by dou J by dou J prime, dou I prime by dou K by dou J prime. So that is exactly what we have here. Now this is nothing but, from this expression, when you consider this expression, this is nothing but the partial derivative of dou I prime as a function of a function with respect to, so this is something we have written it here. So this J2 is nothing but the I prime as a function of a function with respect to the partial derivative of I prime as a function of a function with respect to that of J prime. Now when you consider the right hand side of it, what we end up having is, we have an independent variable I prime. So here we need to have this differentiation of dou I prime with respect to dou J prime. I prime is an independent variable, J prime is an independent variable, so this leads to 0, and ultimately we will end up having an expression 0. Now this operation, when we repeat sufficient number of times, then the product of Jacobian 1 and 2, which involves the coordinates I prime, J prime and K prime, and I, J and K, will give us an identity matrix of 3 cross 3 size, or a 3 cross 3 identity matrix. Now it means J1 is the inverse of J2. So what essentially we have arrived at is, it's just not the known matrices of R and theta. So the R and theta, these are known, so the known matrices of, or the known coordinate systems of polar and Cartesian. So this involves R and theta, a well-defined coordinates, X and Y are well-defined coordinates. Now the derivation that involving the inverse, the derivation that establishes the inverse relation should not stem from the definition, the definition that we have already attributed to each of these coordinate systems. So we should not concede that, or this inverse relation should not stem from the definition of the coordinates that we have already attributed to it. So when we consider R and theta and X and Y, the reason we started off from that is because it is easy for us to rather understand what is happening and how one is inverse of the other. Now the other discussion involving I, J and K, we did not have any definition attributed to it. It could be linear, or it could be rather orthonormal. It could not be orthonormal. It could be different. So we did not have any predefined. We did not have a clear definition attributed to it. We did not clearly define what each of these coordinate axes meant. But despite this generic nature of these axes of the coordinate system, what we were able to establish is, when we are able to express the coordinates of each system in terms of the coordinates of the other, then it is possible for us to show that when we are able to express one as the coordinate of other, and when we are able to treat one as a function of a function and recover the corresponding variable, then it is possible for us to show that the Jacobian of one coordinate system is rather the inverse of another coordinate system. So we started off, to put it all together, we started off with two known coordinate systems, R and theta. So the coordinates of one of the system can be expressed as the coordinates of another system. So based on these relations, we were able to show that the product of the Jacobian of these two coordinate system yields an identity matrix, meaning the Jacobian of one coordinate system is the inverse of the Jacobian of the other coordinate system. Now this is not necessarily true when we have a definitive definition associated with, when we have a precise definition associated with, or a predefined characteristic associated with these coordinate system. Even when we consider the generic coordinate systems of I, J and K, I prime, J prime and K prime, and if we assume that we are able to recover the coordinates by treating it as a function of a function to the recover the corresponding independent variable from the function of a function, if we start from that point and we consider the generic coordinate system, which we know nothing about, I, J and K, and I prime, K prime, J prime, we have shown that the Jacobian, the product or the Jacobian of these two coordinate systems, Jacobian again is nothing but it compiles all the partial derivative. It expresses all the partial derivative of the coordinate system with respect to the other coordinates of the other system. When we consider these Jacobians that express the partial derivative of one coordinates with respect to the coordinates of the other system, we were able to show that the product of these two Jacobians are identity matrix. So one Jacobian is rather the inverse of another Jacobian. Now, if we are able to attribute a significance to this Jacobian, if we are able to show that these Jacobians are just not a numerical operation, but it has a significance associated with each coordinate system. Supposing if we are able to show that the Jacobian, these Jacobians, they rather capture the unit vectors of each of these coordinate systems, then we will be able to establish the relation between two unit vectors. Let me repeat, instead of seeing these Jacobians as just a numerical operation, these Jacobians as the combination of partial derivatives of the coordinates of one system with respect to the coordinates of other system, instead of just having that understanding of the Jacobian, if we are able to show that these Jacobians rather they capture the unit vectors for a given system, and we are able to show that there exists a relationship between the inverse relationship between one Jacobian and the other Jacobian, what essentially we have achieved is we have established a relationship between the unit vector that describes one coordinate system and the unit vector that describes the another coordinate system. So once we are able to establish this relation between the unit vector of one coordinate system to that of the another coordinate system, then it becomes possible for us to express a vector in such a way that it is independent of the coordinate system. So what essentially our next step is going to be is to attribute a physical significance to what this Jacobian is. So we have so far established that when we have two coordinate system, and when it is possible for us to express one coordinate system in terms of another, when it is possible for us to express or treat a given coordinate of a system as a function of the coordinates of another system and recover its corresponding independent variable, then the Jacobian of the coordinate system is inverse of the Jacobian of the another coordinate system. And now if we are able to attribute a significance to these Jacobians, then we will be able to establish a relation that involves, when we attribute a significance to these Jacobians, we will be able to establish a relation that is based on this physical significance. With this, we will wind this lecture up and we will try to establish, or we will try to understand what could be the physical significance, or what could be the significance that could be attributed to this Jacobian in the subsequent lecture. Goodbye.